As we continue our journey into CMOS logic design, today's focus will be on complex CMOS logic gates, specifically the AOI and OAI structures. Up until now, we have seen how simple logic gates like NAND, NOR, and inverters form the building blocks of digital systems. But when we move towards practical and large-scale VLSI design, efficiency in terms of area, speed, and power becomes crucial. AOI and OAI gates are powerful because they allow us to directly implement Boolean functions in sum of products or product of sums forms within a single logic stage, eliminating the need for cascaded gate structures. This not only makes the logic faster but also significantly reduces parasitic effects and silicon area. Now we would cover the transmission gates and complementary pass-transistor logic, corporal-based methodology for circuit design. Building upon the pseudo-NMOS concept, where we simplified the pull-up network, we now move to a more versatile device called the CMOS transmission gate. Unlike a standard CMOS logic gate, a transmission gate acts as a controlled bidirectional switch. Structurally, it consists of an NMOS and a PMOS connected in parallel, with their gate terminals driven by complementary control signals. When the control input is high, both transistors turn on, establishing a low-resistance path between two nodes, A and B. Conversely, when the control is low, both devices switch off, leaving the connection in a high-impedance state. This high Z state is particularly useful in isolating circuit blocks and enabling multiplex designs. Before we go deeper into applications, it's important to understand why transmission gates are so powerful. A single NMOS transistor can only pass a strong 0, but it suffers from threshold drop when passing a 1. Similarly, a PMOS passes a strong 1 but produces a weak 0. The transmission gate solves this problem by combining both devices in parallel, with complementary gate control. Together, they form what is effectively an ideal bidirectional switch that can pass both logic levels strongly, with no degradation. This is one of the fundamental reasons TGs are so widely adopted in VLSI. In practical CMOS implementation, the substrate connections are important. The NMOS device is tied to ground while the PMOS is tied to VDD. Depending on the operating voltages, both devices may experience body bias, which affects their threshold voltages and conduction behavior. Designers must account for this effect when analyzing transmission gate performance. In circuit schematics, you may see different symbolic representations of the TG, but fundamentally they all denote the same parallel NMOS-PMOS pair with complementary gate drives. Looking at the truth table of operation, when the control signal C is high, its complement is low. This ensures that both NMOS and PMOS devices are turned on, creating a low resistance path between A and B. When the control is low, both devices turn off and the path is open, a high impedance state. What makes TGs unique is that they are fully bidirectional. The signal can flow either way depending on the circuit requirement. To better understand transmission gate characteristics, we analyze its DC behavior across 3 operating regions. The biasing of NMOS and PMOS in TG are depicted in the figure. As per this, the voltage levels and current are also self-explanatory with knowledge of the subject gained till now. In the first region, when output voltage is below the absolute value of the PMOS threshold, both devices operate in saturation. As the output rises into the intermediate range, the PMOS transitions into the linear region while the NMOS remains saturated. Finally, at higher output voltages above VDD-VTN, the NMOS effectively turns off, leaving only the PMOS conducting in its linear region. In each region, the device can be modeled using equivalent resistances, allowing us to approximate the overall conduction path as a parallel resistance combination. One striking observation from this analysis is that while the individual resistances of the NMOS and PMOS vary significantly with output voltage, their combined effect is almost constant. The parallel connection of both devices flattens the resistance curve across a wide voltage range. This property makes the transmission gate highly attractive for circuit designers, because it can be modeled as a nearly ideal switch with an equivalent resistance for dynamic analysis. Such modeling greatly simplifies timing and power calculations. Transmission gates are much more than theoretical switches. They form the backbone of many practical circuits. The most common use is in multiplexers, where TGs allow a compact implementation compared to standard CMOS logic. In sequential logic, TGs are fundamental. A simple level-sensitive latch can be built using a TG and an inverter. By cascading two such latches, we get an edge-triggered flip-flop. They are also used in arithmetic logic circuits for efficient XOR and multiplexing operations. And in large SoCs, TGs play a crucial role in bus switching and routing. A simple but powerful application of transmission gates is in multiplexers. A 2:1 multiplexer can be implemented with just 2 TGs. The control signal S determines which input is connected to the output. When S is logic high, the lower TG conducts and routes input B to the output. When S is logic low, the upper TG connects input A instead. This implementation is more compact and efficient compared to standard CMOS logic realizations, and it also preserves full voltage swing thanks to the complementary action of the devices. Another classic use case is the XOR gate. Using 2 TGs and 2 inverters, we can realize the XOR function in only 8 transistors. With further optimization, the transistor count can be reduced to 6. This highlights one of the biggest strengths of TG-based logic: compact realization of complex Boolean functions. Such designs are particularly beneficial in arithmetic circuits, where XOR operations are fundamental building blocks in adders and parity generators. Expanding on this, we can construct generalized TG logic circuits that directly realize Boolean expressions. For each input combination, at least one TG path must conduct to avoid leaving the output floating in high impedance. This requires careful design, often using both inputs and their complements to control the TGs. For example, a 3-variable function can be built with about 14 transistors, including the required inverters. Though the count seems higher, the structure is compact and flexible compared to traditional CMOS implementations. Finally, from a physical design perspective, transmission gates introduce layout challenges. Since each TG has both NMOS and PMOS, multiple N-wells are typically required. If realized naively, this significantly increases the overall area. A common optimization is to place all PMOS transistors into a single shared N-well, reducing area at the expense of more complex routing. Designers must strike a balance between transistor sharing, routing density, and well isolation. These considerations ensure that TG circuits remain area efficient in practice. Despite their advantages, transmission gates are not without challenges. They always need a complementary control pair, which increases routing complexity and requires additional inverters. Also, although TGs act as near-ideal switches, the output usually requires buffering to drive higher fan-out. In VLSI layout, careful optimization is necessary to minimize parasitics from the parallel NMOS and PMOS structure. Thus, while TGs are indispensable, their practical use requires design trade-offs. Let us discuss complementary pass-transistor logic, corporal. Having explored the versatility of transmission gate logic, we now move toward another design style that aims at reducing complexity: complementary pass-transistor logic, or corporal. The motivation for corporal comes from the observation that full CMOS passgate logic circuits require both NMOS and PMOS devices, which increases complexity and loading capacitance. Corporal simplifies this by relying solely on NMOS pass-transistor networks for the actual logic operation. However, to make this work effectively, each input must be applied in both true and complement forms, and the circuit naturally generates complementary outputs. These outputs are then fed into CMOS inverters, which restore proper logic levels before driving subsequent stages. The structure of corporal is highly modular. Every input is provided in its true and inverted form, which allows the pass-transistor network to operate efficiently. Within the core, only NMOS devices are used, which keeps the capacitances of the internal nodes low. As a result, transitions occur faster compared to CMOS or TG-based logic. On the output side, corporal does not directly drive the next stage. Instead, it produces a pair of complementary signals, and these are passed through CMOS inverters for full swing restoration. This modular input-output symmetry makes corporal suitable for building more complex arithmetic circuits with consistent design patterns. One of the strongest advantages of Corporal is speed. By eliminating CMOS devices from the passgate network, the circuit significantly reduces parasitic capacitances. This reduction directly improves transient response and enhances speed performance. Furthermore, since Corporal inherently uses complementary inputs and generates complementary outputs, it fits naturally into modular arithmetic structures like adders, multiplexers, and comparators, where both forms of signals are already required. This design style thus provides a balance of compactness and high-speed operation. However, these advantages come with certain drawbacks. A fundamental issue is the threshold voltage drop across NMOS devices. To eliminate this, Corporal requires special threshold adjustment implants to reduce the effective VT close to zero. While this enables correct logic transfer, it increases process complexity and reduces overall noise immunity. As a result, Corporal circuits are more prone to subthreshold leakage when devices are in the off state. Thus, although faster, Corporal designs can face robustness challenges, particularly in deep submicron technologies. To illustrate, let us consider Corporal implementations of basic gates such as NAND 2 and NOR 2. Each of these circuits requires about 8 transistors, with inputs applied in complementary form. The Pass-Transistor core performs the logic function, while CMOS inverters provide restored complementary outputs. Although transistor count is not drastically lower compared to conventional CMOS, the speed and modularity benefits make Corporal favorable in certain applications, especially arithmetic units. Let us first examine the NAND function in Corporal. The network requires both true and complementary inputs. Using only NMOS pass transistors, we construct a logic network that passes the appropriate signal depending on the combination of A and B. For example, when both A and B are high, the logic path enables a low signal to propagate, generating NAND equals 0. In other input cases, the pass network ensures that a high is passed. The beauty of Corporal is that the complementary output is also generated simultaneously. Finally, CMOS inverters at the output restore the signal levels, removing any threshold drop. The transistor count for NAND in Corporal comes to about 8, not significantly less than full CMOS, but faster due to reduced parasitic loading. Now let us consider the NOR gate in Corporal. Again, complementary inputs are mandatory. The pass-transistor network is arranged so that if either A or B is high, a 0 is passed to the output, thereby realizing NOR. The complementary output is produced at the same time. As with NAND, static CMOS inverters are required to restore full voltage swing. What distinguishes Corporal is its speed. By eliminating CMOS devices inside the pass network, we reduce internal capacitances, which accelerates signal propagation. XOR and XNOR are particularly well suited for Corporal design. Using around 8 transistors, similar to a CMOS implementation, Corporal can realize XOR functions more compactly due to its complementary nature. To further speed up the output, cross-coupled CMOS pull-up devices are sometimes added at the inverter stage. This improves the rise time and ensures balanced signal transitions. Since XOR is central to arithmetic blocks like adders and parity checkers, Corporal offers a practical advantage here. Among all gates, XOR and XNOR benefit most from Corporal. In CMOS logic, XOR is relatively expensive to implement, often requiring 12 transistors or more. Corporal reduces this to about 8 to 10 by using a clever pass-transistor structure. The NMOS network selectively passes A when B is low, and passes B when A is low, exactly implementing the XOR function. Since the circuit is complementary in nature, we get both XOR and XNOR outputs in parallel, which is very convenient in arithmetic logic circuits. This makes Corporal especially attractive in data path designs like adders and multipliers. Now, where does Corporal actually find use? Its strength in implementing XOR, multiplexers, and adders makes it highly relevant for data path circuits such as arithmetic logic units in microprocessors. Whenever high performance is prioritized over ultra-low power operation, Corporal becomes a favorable choice. For example, high-speed adders in processor ALUs often employ Corporal structures because the delay improvements outweigh the penalty in noise immunity and leakage. However, in ultra-low power IoT or battery-operated systems, Corporal is avoided since static leakage and process complexity are less tolerable. This context helps us understand that Corporal is not a universal replacement for CMOS, but a specialized design style tailored for high-performance computing. To summarize, complementary pass-transistor logic offers a compelling design alternative to transmission gate logic and conventional CMOS. Its strengths lie in high-speed operation, modular design, and suitability for arithmetic circuits. Yet, these benefits come at the cost of reduced noise margins, higher susceptibility to leakage, and increased process complexity due to threshold adjustment. Thus, Corporal is a design style best employed in performance-driven data path applications, where its speed advantage can outweigh the associated trade-offs. To place Corporal into context, it is important to compare it with other logic design styles. Full CMOS is still the most robust, offering excellent noise margins and zero static power dissipation, but at the cost of higher parasitic loading and area. Transmission gate logic improves signal integrity but doubles the transistor count because it requires both NMOS and PMOS in parallel. In contrast, Corporal offers a high-speed alternative with reduced capacitance and modularity, but its reliance on complementary inputs and its reduced noise immunity are significant drawbacks. The choice among these depends on whether speed, power, area, or robustness is the primary design goal.